Hello everyone, in this video, I'm going to present my latest work titled on the numerical solution of Burger-Fisher equation by the Modified Strang Splitting Method. First, let me introduce myself. My name is Dadang Amir Hamzah from Presentatio University. This is the outline of my presentation. I will start with introduction, explaining Modified Strang Splitting Method, application and result, and reference. Let's start with introduction. Splitting method are numerical method for solving evolution equation. The idea is to decompose the equation into several parts and construct an approximate solution by combining the time integration of each split equation. There are several splitting methods such as the Lie splitting and Strang splitting. They differ in the way of combining the solution of each split equation. According to McLachlan and Quispel, the Strang splitting is second order and Lie is first order. Now, consider the one-dimensional semilinear parabolic equation of the following form. This is the general form of reaction-diffusion equation, when the first part is the diffusion term and the second part is reaction term. If the reaction term is combination between Fisher and the Burger equation, this problem 1 until 4 is called Burger-Fisher equation. In this video, we are concerned with numerical integration of the above equation. The straightforward decomposition of the equation 1 seems the following two equations, that is Vt equal the diffusion term and Wt equal the reaction term. Suppose that these equations are well posed, at least locally. If pH and CH are time evolution maps for the first and the second equation respectively, then the Strang splitting method is formulated as follows. As we can see, the Strang splitting method is a composition that maps un to un plus 1. This composition can be switched between C and P maps, where in here H is the time steps. The problem that appear from this arrangement is the order of reduction. That is, the second convergence is not achieved. For example, if f is a function that depends on u, then the decomposition V in equation 5 is heat equation. However, the W equation is not compatible with the boundary condition, except for the case the derivative of f equal to the reaction function. This incompatibility could cause the order reduction. Order reduction also occurs for other type of equation, such as advection diffusion equation, and other cases can be seen on Hundsdorfer and Verwer. Now let's continue to Modified Strang Splitting Method. Einkemer and Osterman proposed a new splitting method which they called the Modified Strang Splitting Method that overcome the order reduction in multidimensional setting. The key idea is to devise the decomposition after a certain of change of variables. Convergent analysis also given in their paper. Nakano et al. Applied this new approach for Burger's equation, that is the reaction term in the form of ux. Following Nakano's work, we will apply this method to the Burger-Fisher equation. To do so, let us rewrite the equation 1 to avoid the non-homogeneous boundary condition. For this aim, introduce a new variable z as follows. If we observe, when we put x in the boundary, it will compatible with the boundary condition that we have. And this is the solution of Laplace equation with the boundary condition same with the original boundary condition in the Burger-Fisher equation. Now let us define a new variable u tilde as u minus z. Then the problem 1 can be transformed into the following form. And to avoid the incompatibility with the boundary condition, Nakano considered the following decomposition. The compatibility of W equation with the boundary condition is achieved, and the explanation can be seen in Nakano's paper. Now, let's define the scheme for modified strang splitting method. The scheme is not different from the original one. However, now we apply the decomposition that defined by Nakano, and the equation is from the transformed, or that we have rewritten in the u tilde form. Let's continue to application and result. Consider the equation 1, the following reaction term in the interval x from 0 until 10. We choose the spatial discretization and x equal 50 with delta x 0.2, and for time discretization we set nt equal 50,000, and the time discretization is, or the time step is 1 times 10 power minus 4. The first derivative and that appear in the equation is approximated using forward difference, and the second derivative is approximated using centered difference. For the time integration, we apply Euler method, and we apply a strang splitting and a modified strang splitting and compare the result. The result is compared with the exact solution, and the accuracy is calculated using maximum absolute difference. That is, the maximum of absolute difference in each spatial partition is taken, and it's applied to each time step. We choose the following initial condition and boundary condition. The problem 1 with the following condition has the following exact solution, and then we can see the result as follows. The red line is the strang splitting method, while the blue line is the modified strang splitting method. At glimpse, we see that the modified strang splitting method has larger error than strang splitting method. However, at some point they have the same accuracy, where in the x-axis here is the time step, or number of time step here, and here's the value of error. From the following result, we remarks the following. The modified strang splitting has the same order with strang splitting method, that is the second order of accuracy. The significance of the odd method is not yet seen in this example. We suspect that this phenomena has relation with the Courant-Friedrich-Lowry condition, when the relation between time and spatial step need to be considered. The time integration also has contribution, as well as the decomposition procedure. Those mentioned suspicion is the topic for our future work. Here's the reference that we use. And that's all for me. Thank you for your attention.